Okay, so I'll just be talking today about sort of projects that are actually adjacent to our main project, which is single particle measurements, but just to just go over some of what we do in our labs, material that I covered last time, but just to quickly put everything in context. So the group itself, the team is myself from McGill, James Davies from UC Riverside, and then Allison Bain from Oregon State. And our groups primarily do single particle measurements. Allison and myself, we use optical trapping, and then James uses the electrodynamic balance. And the reason why to look at aerosols at the single particle level is there's the obvious reasons that when you don't have a size distribution, you no longer have to worry about distributions in size and composition. So the error and uncertainty, those both improve. And then there's also non-obvious reasons, which when you're doing spectroscopy appear, which is these sharp resonances that you get in the, anyone who's ever done a me calculation, and you didn't include a size distribution is probably aware of this. You get these sharp resonances, and they're actually very useful when you're just looking at a single particle because it allows you to size things very accurately and also get out the composition very accurately. And what these platforms look like, if we just go through an example from my own lab, the optical trap, it just uses a focused laser beam to hold a single particle. So the little cartoon there on the far left, and there an actual image of a trap in the middle, where there's two electrodes there just for reference, but you can see the focus beam, and then if you zoom in and filter out the green light and you just use an LED to look at it, you can see the optically trapped particle there between the two electrodes, which play no role in the optical trapping, but provide scale. And so you have this trap, and then you build a whole cell around it to control the most important parameters, of course, in the atmosphere: temperature and relative humidity when we're studying droplets. So we have that as an example here, and then we can just do measurements on it, again, using spectroscopy. So we can use, the main tool that we use in my lab is actually inelastic light scattering, so Raman scattering. So we see the water band here in the red with the whispering gallery modes, or the MDRs for the spherical particle on top of that. We can also use angular light scattering. That's very easy to collect from just in this case, the green trapping laser. We can just get the me fringes and use that to characterize the particle as well. It's not as great as the MDRs though. And in James's lab, they use the EDB, and so they use just elastic light scattering because they don't have this intense light source with the Raman scattering. So they use that to characterize both non-absorbing and absorbing particles. One advantage to this setup when you don't hold a particle with light is you can trap things that absorb a lot of light. And they also have this coupled to a mass spec, so they can, at different time intervals, they can trap multiple particles and then send them off into the mass spec, useful for studying chemical transformations, of course. So as I mentioned last time, we've used these techniques over the many years to study all sorts of different physical processes in the atmosphere. And when we're studying these, because our measurements are all based around sizing and refractive index, we're always getting a wavelength-dependent refractive index, and that's very useful in the context of SRM. So that's, I guess, where my first topic comes in, which is when we have these refractive index measurements, we want to assess the RI in the context of SRM, like how, for a particular wavelength-dependent refractive index, what that actually means in terms of solar radiation management. And the quantity that we are going to use and I'll discuss today is just the change in the bond albedo. So this just is very useful tool for comparing different refractive indexes, but just different aerosol particles in general, because if we just look at the definition of this quantity, which is telling us how much light is reflected away from Earth's atmosphere when you add the aerosol in question, we see that it has the single scattering albedo, the optical depth, so there's concentration in there, and then also the isotropic upscatter fraction, which, so the main thing here is the phase function, capital P, is buried inside of there, and that'll have the refractive index information in there along with other particle properties. So those three quantities are all in that integrand, and then along with the spectral solar irradiance. So this thing just captures all the aerosol properties, and if we were just to look at it in the context of a very simple radiative forcing calculation, we can see one of the nice things you can do is you can just separate out all the aerosol properties into that big delta A. So size, refractive index, shape, structure, concentration, size, they're all just separate from the other in the simple calculation, the geophysical variables there. So that's what we'll be looking at. And if you just do a simple calculation for this with a constant refractive index as a function of size, So we do one of these heat plots here with delta A. What we see is, because it's just a single wavelength, there's a bunch of fringes associated with resonances. But if we just track the maxima as a function of the real part of refractive index, the imaginary part here is 0 for the moment. What we see is that as the refractive index increases, basically you get the main peak for delta A just goes up and sort of levels off around 0.1. It doesn't seem to go to smaller sizes beyond that. So this is something that's already come up multiple times today, is that the optimal size is around 100 nanometers. So we see that here. But this is just for monochromatic radiation. If we then include the entire solar radiance spectrum, the top of the atmosphere, what we see is all those sharp fringes that they disappear, and we just have a more broad peak. However, the peak location doesn't actually change that much from this compared to the monochromatic result as well. And we can also just calculate the delta F for this as well if we wanted to. So the first thing we can actually understand with this calculation is why it is that 100 nanometers in radius is the optimal size, or just about there. And we can do that by just looking at, again, the things that are inside that integrand, those three terms there. The most important parts, just captures all the aerosol information. If we look at the full calculation here, which is the light blue, and then if we just look at the two dipolar modes, the magnetic and electric dipolar modes, so the darker blue and the red, if we look at those three things behave as a function of size, what we see is, at a high refractive index 3, as you increase the size from, in this case, 50 to 100 nanometers, all the dipolar modes, they just shift, and they align pretty well with the peak in the solar irradiance here, right? And as the size continues to increase, those dipolar modes, which are actually the best for the upscatter fraction, those shift out of the visible, and then they just continue to shift into the near infrared. So they're just not, there's just not as much intensity there. In these higher order multiples, they just don't scatter as efficiently. The upscatter fraction just isn't as efficient. So that's the reason why this optimal size just comes out to be around 100 nanometers. You can play the same game with refractive index. It's just once you get the really high refractive indices, in that case, everything blue shifts. It's just much less sensitive to changes in refractive index. So going to really, really high refractive index, it just doesn't pull it back as much in that case. OK, so we can look at other things as well as we move away from this sort of monodisperse aerosol. If we look at a size distribution, a very narrow size distribution, basically no change here in the delta A. But as we increase the size distribution in this case, so more typical, the peak delta A goes down, and then also the peak location shifts to smaller sizes, and then eventually for a very broad distribution in this log normal distribution, it shifts to even smaller sizes here. Okay, so that's size distribution. What about the imaginary part of the refractive index? This is something I was curious about from discussions last time. And what we see is as K goes up from 10 to the negative 6, 10 to the negative 3, 10 to the negative 2, not much change. But then from 10 to the negative 2 to 10 to the negative 1, there is starting to be a dip in the delta A. And then once you get to a K of 1, then it's greatly diminished. When you go to really high K, like 10, then at that point your dielectric is now a conductor and it's starting to reflect, so it goes back up. So it doesn't just go down indefinitely. But so we see that basically like 10 to the negative 2 or less doesn't seem to be that significant, at least for this quantity. And I should just, I guess, emphasize we're just looking at shortwave radiation here. OK, so what about dispersion? So everything up until this point has been a fixed wavelength. What about when the wavelength varies with or the refractive index varies with wavelength? How do we handle that? So I'm just using this data set from Frank Koich's paper for these 8 materials here. And so here's the real part and then the imaginary part that they have in that data set. And if we just run these calculations, so just as a function of radius, and the refractive index is now just determined by, so this is the solar radiance spectrum. The refractive index is now just determined by those functions across the visible and beyond. So what we see here for the titanium dioxides, the rutile and the anatase, it does, including dispersion, so the wavelength dependence of the RI does lead to some change in delta A, right, noticeable. But for these other materials here, as you go down, it's less significant. It can basically be neglected in those cases. But if you want to be quantitative for these titanium dioxides, it does matter. And if we go back to the real part of the RI, we can see why that's the case. For rutile and anatase, the RI is, when we go across the peak here, it is decreasing, changing quite a bit, the real part of the RI. So that's why there is a dispersion does matter in those cases, whereas these other ones, it's much more flat. So you can just pick the RI at 550 nanometers and you're good in that case. Okay, so that's dispersion. Core shell particles. Another question that I guess that came up, in my mind at least, at the last meeting was how coatings affect the optical properties of particles. And so if we just take one of these high index particles and then we start to we add a water coating to it and increase the thickness, what we see is, so down here with 0 thickness, the optimal size is about, again, 100 nanometers. As you add a pretty thin water coating, delta A just falls off pretty quickly. Like once you're at like a 10 nanometer coating of water in this case, your optimized particle has been basically completely spoiled by this water coating. So that's an interesting result. And then another aspect with these core shell particles that we can consider is what happens if you have a low index core and then a high index shell. And this would be useful because one of the issues with these high RA particles is that they tend to be very high densities, so they're heavier particles. And if you had a lower index core, then that would be, you could have a composite particle that's overall lighter. And what we see here is that, yeah, you can have this low index core, and the shell thickness can get to about this. And really, if I just go along this red peak here, delta A is not really changing that much. So this is optically equivalent to this case down here. And then as you go up further, delta A starts to fall off until eventually, of course, at the top, it's completely gone, or it's back to nothing, basically. So essentially, these composite materials can lead to lighter particles, and we can just do a pretty straightforward calculation, which is just calculate the settling velocity for this. And we see that, if you have really light cores, then indeed you can reduce the settling velocity, but have optically, equivalent particles to these, to the heavier homogeneous version. All right. Another, I guess, idea, since we're just playing around with core shell particles, what if it's possible then to take two materials, combine them into a new particle where the optical properties are better than the two homogeneous components? So if you're just looking at scattering from a single wavelength, that's actually very easy to achieve. I won't go into how this plot works, but basically, like at these really high refractive indexes, you have the peak there, but there's also a peak over here where you can mix these two things together in a core shell structure and get a better reflector. But these effects are largely due to, again, these Mie resonances. So when you actually have irradiation by many wavelengths, that's completely gone, and it doesn't seem to be achievable with at least spherical core shell particles. So going forward with this work specifically, we'll be looking at non-spherical particles as well. I mentioned last time our previous work with T-matrix, so we'll be using that. The main thing that we need to, if we want to just keep using delta A, we need a orientationally averaged phase function quantity. So both for these, the scattering cross sections or the scattering efficiencies and the extinction efficiencies, these orientationally averaged expressions, they already exist for T-matrix, like in the Mashenko book from 2002. But if we're just looking at the orientationally averaged phase function, that's typically, or to my knowledge, is only done numerically with like Gaussian quadrature. So we would be interested in developing that, and we've made quite a bit of progress on this. So hopefully we'll have an analytic expression analogous to those other ones pretty soon. And specifically, we've just been looking at the orientationally averaged asymmetry parameter, because you can use, of course, this Henyey-Greenstein function, which has that G in it, and that actually does a pretty good job for approximating the full Mie calculation there in that there. So that's where that work is. So just to change gears here in the last several minutes to a different topic. So this project started about 4 months ago, but has progressed very, very rapidly. So at McGill, we have this alternative fuels lab where they look at using metals as recyclable carbon-free high-energy density fuels, as I said there. And that's interesting. So we see some of these burning here in the lab that they have. What's more interesting, though, is that these fuels, these metals, when you burn them, you produce metal oxide particles. And I thought that was interesting. So Jeff Bergthorsen, the professor who developed this alternative fuels lab, I asked him to see some of these SEM images for these particles, if they could get them. And then he sent me some of these for these metal oxide particles that are burning in these metal flames. And we see the typical sizes that they have here. So that's pretty, in this sort of around 100 nanometer range, or even smaller in this case. And then also, if just getting familiar with this literature, some of the metals that they work with, we see here that titanium and then, of course, aluminum, which I just showed, that was an SEM of that. Those are both potential. They've shown that they can burn these, and so those are both potential fuels. So they have access to a lot of metals that are viable to produce oxides from just burning them. Some of these other ones are listed as being too expensive or produce toxic oxides in that case. And this isn't just like some hypothetical thing for just burning these and actually using them as fuels in, say, an aircraft, as you would if you were interested in SAI. People have shown already that you can replace. So solid rocket propellant is already made of alumina. It's just very, very large alumina particles. People have shown before that you can use nano-sized alumina particles, and they've even launched rockets using these propellants. That their motivation for this was more in line with just increasing the rate of how fast it burns. So this is viable, and the nice thing about this, or the appealing thing about this, is a lot of rockets using these solid-based alumina fuels. They're already going through the stratosphere. They're already injecting particles, these, say, aluminum oxide particles. It's just that they're not optimized. So why not optimize them? So that's where this project came out of. And this is just being done in collaboration, as I said, with this alternative fuels lab in McGill. So here's just the system that they've developed over almost 2 decades now, where you have the metal powder, and then you just push it up through this, and you mix in air, and then you just burn it. And so you can see here the actual, what they call this Bunsen dust burner. They're just imaging it there with this camera. And a lot of the stuff that they're interested in is actually just the combustion process itself and studying the mechanisms of this and the particle growth. So it's a pretty interesting setup, if I could just say a few words about it. So yeah, they're burning it, and then they can just move this platform up, so they can just take a picture of the flame, of course, but they can also do atomic emission spectroscopy. And so what you see when you do this is things like this. So you have your solid alumina, it then gets really hot, turns into a liquid, and then eventually vaporizes, and you can actually see the atomic lines for alumina being emitted there from the vapor. It's so strong, and then some colder aluminum atoms are actually leading to the dips in the peaks there, the self-reversal region there. And we can even see some intermediates in the combustion process here, with aluminum becoming aluminum monoxide here during the combustion process. So we can see that we no longer have, I guess, atomic emission. We now have a molecular emission spectra, because we have the vibrational and then, I guess, the rotational bands on top of this here in this particular image here. And so what we've been doing with Jeff is they can just take their flame, and they can actually just put a collection plate right above it, and then just collect a bunch of this sample. And then we can characterize it. I already showed an example with SEM. So here's an example that we recently got. So just SEM, there's the particles, and there's the size distribution here. But of course, we can use FTIR. We've just been using ATR, FTIR. And then also UV-Vis, near-IR, is more complicated, because we've mainly been using diffuse reflectance to characterize that. And then also, we've been trying ellipsometry as well, but hopefully there's better techniques that exist out there. So we've been using that to characterize the complex refractive index across basically from the UV to the far infrared. With the results look okay, I'd say at this point, but I'm not going to show them here. So yeah, the overall just appeal of the approach is you have in situ particle generation, right? Because it's just coming out of the thrust of the rocket. Many SRM candidate materials are viable. Optical particle sizes, I believe, can be achieved. We're already pretty close. And modifying existing fuels, like just changing existing aluminum propellant, is very practical, I would think, to implement. Okay, so that's basically what I wanted to talk about today. Just for the 2 projects I discussed, to summarize, the change in the bond albedo project, all those calculations I showed, those were done by Benjamin Benz, who's here. And if you're interested in T-matrix, you can talk to him about that. And then also the combustion of metal fuels was done by Lana and Ellie. So thanks for your attention.